to talk about factoring special products. Sometimes we have binomials or trinomials that have special qualities about them, and we can factor them maybe in like a shorthand kind of way. So first off, let's talk about difference of two squares. So this is when I am given a binomial where there is a perfect square in the front, a perfect square in the back, and a minus sign in between. So for example here, I have a squared. That's a perfect square. Remember, anything that can be written with an even exponent would be a perfect square. So squares are definitely perfect squares. And then I have a b squared at the back. If I were to take the square root of that front, which is a squared, that would give me a. That's going to go in the front of both of these binomials. All right, and then if I were to take the square root of the back, which is the b squared, that would give me b, and that goes in the back of both of these binomials. And then there is always a plus and always a minus. That's because if I think about this, for example, let's look at this like x squared minus 9. Normally, I have something more like x squared plus 6x plus 9 or something. All right. And I have three terms. I have an x squared, a 6x, and a 9. The thing is, this doesn't have a minus or a middle term. It doesn't have the x. So I'm missing that. So if I thought about this in terms of the way we've learned to factor, I could say, well, I'm adding nothing to the middle. So if I factored it like I normally would, I could say, well, I'm looking for, I'm going to have a positive and a negative, my x, and I'm looking for two numbers that are going to multiply to make the 9, that are going to subtract to make 0. Well, I have 1 and 9 and 3 and 3. Well, that would be 3 and 3. Now, if it helps to visualize that and factor it that way, you can. Or you could say to yourself, all right, I have a perfect square in the front, a perfect square in the back, and a minus sign between. So I immediately know that this is the difference of two perfect squares. I know that I have a positive and a negative, and if I took the square root of the x squared, that would be x, and it goes in the front. And if I took the square root of the 9, that's 3, and it goes in the back. And then my two middles cancel out. All right? That's because these two binomials are what we call conjugates. They are exactly the same, except the sign that is in the middle between the front and back terms is opposite. So if I take a look at number 1, okay, I have x squared in front. That's a perfect square. I have 25 in the back. That's also a perfect square. And I have a minus in the middle. That means that I have two perfect squares, and I know that when I have two perfect squares with a minus sign, it automatically factors into two binomials that are conjugates. So if I take the square root of the x squared, that gives me x. I know that goes in the front. I know that these are conjugates, so one is a positive, one is a negative. And if I take the square root of that back number, I get 5, and that goes in the front and the back. So if you take a look at number 2, you not only have to make sure that your leading coefficient is a perfect square, but also that the variable behind it is also a perfect square. 1 is a perfect everything. So 4 is a perfect square, x squared is a perfect square, 1 is a perfect square. I have a minus in front of that 1 back there, so I know that this is the difference of two squares. The square root of 4 is 2. That goes in the front. The square root of x squared is x. That goes with it. These are conjugates, so 1 plus 1 minus, and then the square root of 1 is 1. All right, same thing here. We have two perfect squares with a minus sign. So I know that I have a conjugate, 1 positive, 1 negative. The square root of 100 is 10. Since it's in the front, that goes in the front. And the square root of m squared is m, and that goes at the back. All right, number 4 is a little different though, because I have x to the 4th plus 25. I don't have a minus in between these two perfect squares. And if you think about this, I don't have an x, I'm missing that. The only thing that multiplies to make 25 is 25 and 1 or 5 and 5. Neither of those will add to make 0. So therefore, this can't be factored. So can't be factored. You really have to pay attention because, you will come across things that can't be factored and you need to know when they can't be factored. Now, as with factoring everything, you should always look for a greatest common factor first. And if you cannot find one, then you move on. None of these had a greatest common factor. Okay, we were just practicing the factoring special products part, not the greatest common factor part. Okay, sometimes we have perfect square trinomials. And sometimes it's easier to identify that from the beginning, and sometimes it might be easier to just factor them in the normal way, but we're still going to talk about them. So if I have a trinomial, all right, a perfect square trinomial means that it's going to factor into two of the exact same thing. So let's say I factored something and I got x plus 3 and x plus 3. Well, anything times itself can be written as that thing squared. So when we factor a perfect square trinomial, we end up with two of the exact same binomial. So if you look at the little formulas here, I have a perfect square in the front, a perfect square in the back, and the middle is made up of 2 times the square root of the front times the square root of the back. Now, I actually wrote this wrong here, and I'm just now catching it. These x's should not be there. Okay, I have a typo. I'm sorry. This should just be a squared. Sometimes I get in a hurry. All right, so perfect square in the front, perfect square in the back, and the middle is 2 times the square root of the front times the square root of the back. Notice there is always a plus sign back here because in order to get two of the same sign, you must have a plus in the back. All right, so I take the square root of the front, that goes in the front spots. The square root of the back goes in the back spots. And then you get double of your middle, so it ends up being a plus b squared. It's the same thing with the plus, except there's a minus up front, so the signs are minus instead of plus. So if we want to check for these, this is how we check. We're going to take the square root of the front. The square root of x squared is x. Then we're going to take the square root of the back. The square root of 16 is 4. Then we're going to multiply these two numbers and double them. So 4x doubled times 2 is 8x. And if that is the middle, then I know that I have a perfect square trinomial as long as I have a plus sign at the back here. All right. So that means that this would factor into two of the exact same thing. I see I have a plus, so I look up front, there's 2 plus signs. All right, I already know that the square root of the front goes in the front, and the square root of the back number goes in the back, and I have two of the exact same thing, so x plus 4 squared. Now, I don't have to show all of that work. I could just check it in my head. So, for instance, if I look on 16, this is a perfect square, this is a perfect square, and I have a plus at the back. So I know that both my parentheses will have a minus sign. And I'm going to check the middle. The square root of m is m. The square root of 1 is 1. And I'm going to double that. So m times 2 is 2m. And that is my middle. So I can take and square root the front. That goes in the front. Square root the back. That goes in the back. And I will have two of those because this is a perfect square trinomial. Now, when you have ones like that, sometimes it's easier to just factor like normal and say I have 2 minus signs, what multiplies to make 1, that will also add to make 2, and that would be 1 and 1. So you can factor them like normal, but sometimes you get really large numbers in the front and the back, and it's easier to kind of, factor these by doing the special way. Okay? So let's take a look at number 7. So number 7, I do have a perfect square in the front. 4 and x squared are both perfect. And I have a perfect square at the back. 9 is a perfect square. The square root of 4x squared is 2x, and the square root of 9 is 3. That gives me 6x. If I double that, I get 12x, which is my middle. All right, so I know that I'm going to get 2 of the exact same thing, so I can just write that as a binomial squared. I look up front. I know that both of those binomials would have had a minus sign. I square root the front. That gives me the front, so 2x. And I square root the back. That gives me the back. And I have both of my binomials, so 2x minus 3 squared. All right, on number 8, I see that I have a common factor of 4, so I'm going to factor out 4. 36x squared divided by 4 is 9x squared. 12x divided by 4 is 3x, and 4 divided by 4 is 1. Now I see that I have a perfect square in the front and a perfect square in the back with that plus sign. So I check the middle. The square root of 9x squared is 3x. The square root of 1 is 1. That gives me 3x, and then I have to double that, and I get 6x. But that's not my middle, which means this is not a perfect square trinomial. So instead of factoring it that way, I'm going to have to factor it just like we normally would. So I'm going to take that 9 and multiply it times the back. And then I'm going to say, okay, what multiplies to make 9? 1 and 9, 3 and 3. And I'm looking for the combination that will add to make 3. But the problem is 9 and 1 add to make 10. 3 and 3 add to make 6. Nothing adds to make 3. That tells me that this is something that can't be factored any further. So I just have 4 times 9x squared plus 3x plus 1. And I can't factor that any further.